Hi, this is Hilal. In this video on Mathematical Economics series, we will solve another numerical on the applications of Hessian method in checking the second order condition of a multivariable function. The question is, optimize Cobb Douglas production function, that is q is equal to k to the power 0.3 multiplied by l to the power 0.5 subject to the constraint 6k plus 2l is equal to 384, while q is the quantity, k and l are the capital and labor respectively. We are told to find the critical points and check second order condition using Hessian method. So this is our question, which is based on the constraint optimization, because we have to optimize this function with respect to this constraint. That means it is a question on constraint optimization. Now what will we do? First of all, we form a Lagrange's function. The Lagrange's function is formed. The method is, we take this constraint function. This is our constraint function, so I write here this is constraint function and this is our objective function. First of all, we put this constraint function equal to 0, so I will write here set constraint function is equal to 0. That means we put this whole equal to 0. This will become 384 minus 6k minus 2l is equal to 0. After that, we multiply this function by lambda. So we multiply this function by lambda. That means this will become lambda times 384 minus 6k minus 2l is equal to 0. After that, we form the objective function. Now the objective function is formed by adding the the Lagrange's function is formed by adding the objective function and this resulting constraint function. That is our objective function. We will denote this by q. Our objective function is composed of, that is, this is composed of this objective function. This Lagrange's function is actually composed of this objective function, that is k to the power 0.3 l to the power 0.5, and we add this resulting function with this. So this is lambda times 384 minus 6k minus 2l. So this is our Lagrange's function. So we have formed the Lagrange's function by adding the objective function and the constraint function after multiplying it with lambda. After that, the first order condition for the multivariable function to be at optimum is, we take the first partials of this Lagrange's function with respect to k, l and lambda and set them equal to 0 simultaneously. That is, we partially differentiate this with respect to first k, then l and then lambda. So partially differentiating this, I will write here partially differentiating q with respect to k, l and lambda and set them equal to 0 and set them equal to 0 simultaneously. So first we take q subscript k, means partially differentiating this Lagrange's function with respect to k. So this will become, this 0.3 will become, so I will write with another color. So this will become 0.3 k to the power 0.3 minus 1, that is minus 0.7, and we have l 0.5 here, and then lambda times 384, no k is involved, so this is 0. Now lambda into minus 6k, so the derivative will be minus 6 lambda and set it equal to 0. or we can write this as 0.3 k to the power minus 0.7 L 0.5, and transposing this on LHS, this will become plus 6 lambda. So we have partially differentiated this Lagrange function with respect to k. Similarly, we will partially differentiate this with respect to L, this Lagrange function. Now this will 0.5 will become coefficient, so this is 0.5 k 0.3 L. Now 0.5 minus 1 is minus 0.5. now here it is this is 0, lambda times 384, since no L is involved. Also here no L is involved. Lambda times minus 2L, so this will become minus 2 lambda, and set it equal to 0. So this will become, I can write this as 0.5 k to the power 0.3 L to the power minus 0.5, and transposing this minus 2 lambda on RHS, this will become plus 2 lambda. Similarly, partially differentiating this with respect to lambda, so this will become Q subscript lambda. So here no lambda is involved. Here the derivative of lambda is 1, so we are only with this 384 minus 6k minus 2L is equal to 0. Let this be equation first. We have to solve them simultaneously. Let this be equation second, and let this be equation third. Now to get the optimal values or the critical values, we solve these three equations. Now we divide 1 by 2, this equation 1 by 2. So dividing equation 1 by 2 will give us, this will become 0.3 k to the power minus 0.7 L to the power 0.5, and we divide it by this 0.5 k to the power 0.3 L to the power minus 0.5, which is equal to, here it is 6 lambda divided by 2 lambda. So lambda gets cancelled, 2 1s are 2 3s are 6, so this will become 3 divided by 1 here. Now solving this, now this is 0.3 divided by 0.5, so this will become 3 divided by 5 here. So this is 3 divided by 5. Now we transpose this k to the power minus 0.7 to the denominator. Since bases are same, powers will be subtracted. So this will become, if it is here minus 0.7 is exponent, this will become plus 0.7 is exponent. Now 0.3 plus 0.7 will become 1, so this will become k. Here also we transpose this L to the power minus 0.5 to the numerator, so this will become L to the power 0.5 multiplied by L to the power 0.5. Now 0.5 plus 0.5 is 1, so we get here L, which is equal to 3 divided by 1. So I will here explain a little bit. Since it is here k to the power 0.7, here it was k to the power 0.3. What we did here, we took this k to the power 0.75, since it is here minus 0.75, and we transpose this to the denominator, so there become here k. Now when changing from numerator to denominator, the exponent gets changed, its sign gets changed. So if it was here minus 0.7, this will become 0 points plus 0.7, and it is multiplied with this k 0.3. Since here bases are same, powers will be added, so this will become k 0, sorry, this is here 1 divided by k 0.7 plus 0.3, which is equal to 1 divided by k. This is how we got this k. And similar method is this is for this L. So I hope I make myself clear here. Now we can solve this as, we can write this as L divided by k is equal to 3 divided by 1, multiplying, now transposing, this will become 5 divided by 3. So this is simple maths. I hope you are getting this. So this 3 and 3 gets cancelled. We are with this L divided by k is equal to 5, or L is equal to 5k. So we got L is equal to 5k. We put this L is equal to 5k in this equation. So put L is equal to 5k in third equation. Now putting this will form this as 384 minus here it is 6 and 6k minus 2, and our L is 5k, so I will write here 5k, which is equal to 0. So this will become here, this is 384 minus 6k minus 10k, which is equal to 0. When solving this, this is 6k and 10k, this is minus 16k, that is 384 is equal to 16k, or k is equal to 384 divided by 16, which comes out to be here, when solving this, this is 16 1s are yes, this is here 16 1s are, so this will become 16 2s are 32, so this will become 24. So our k comes out to be 24. So we got the value of k. Now we put the value of k back in this third equation, that is put k is equal to 24 in equation third to get the value of L here. So we write 384 minus 6 into, here k is 24, so I write here 24 minus 2L is equal to 0. Now further solving, this is 384 minus, now 6 4s are 24, 6 2s are 12, 13, 14, so this is 144 minus 2L is equal to 0. This comes out to be, now 4 minus 4 is 0, 8 minus 4 is 4, and 3 here it is 3 minus 1 is, this is 240 minus 2L is equal to 0, or L is equal to 240 divided by 2, which comes out to be 120, implies our L is 120. So this is the value of, optimal value of L. Similarly we can find, so we are we got the value of k and L. So these are our critical pointers. Therefore our critical points are k is equal to 24 and L is equal to 120. So this was the first order condition where we got the optimal values. Now to be sure that these are actually the maximum pointers, we have to check the second order condition, and we have to use the Hessian method. Now we are checking second order condition, that is checking second order condition, that is to using Boarded HESSIAN method, using Boarded Hessian method. Now in the Boarded Hessian method we form a matrix, that is we denote thereby this H, which is composed of the second order partial derivatives of this Lagrange's function, where it is actually it was somewhere here, and these second order partial derivatives are borrowed by the partial derivatives of this constant function. That is, I will write here, it is like this: q k means second order partial derivative of this Lagrange's function, q k l, q l k, and q l l. These are the second order derivatives of this Lagrange's function, and these are borrowed by the derivatives of this partial derivatives of this constant function. So this is c k c l, here it is c k, and here it is c l, and we have this 0 on the principal diagonal. So this is the formula which we use in checking the second order condition. Now we have to calculate the second order partial derivatives of this Lagrange's function. So I will write here, since our qk was, I will write here qk, first derivative was this 0.3, I will write here 0.3 0.3 k to the power 0. minus 0.7 minus 0.7 L 0.5 minus 6 lambda. Now we have to take the second order partials with respect to, that is q k k, that is q k k means second order partial derivative of this will be, now we have to differentiate this equation and this function with respect to k. Now this will become, this is minus 0.7 multiplied by 0.3, so this will become minus 0.21 k to the power minus 0.7 minus 1, that is minus 1.7 L 0.5 minus 6 lambda. Similarly, differentiating this with respect to q k l, now differentiating with respect to l, so this will become with respect to l, this is 0.5 multiplied by 3, so this will become 0.15 k to the power minus 0.7, and L, now 0.5 minus 1 is minus 0.5. So actually here the derivative of this comes out to be, here it is 0 because no k is involved in this. So similarly our q, taking this second equation, that is ql, so we take here ql is given as ql, actually I am getting oversighted here, so I will write here this is 0.5 k 0.3 l minus 0.5 minus 2 lambda. Now differentiating this with respect to l, that means taking partial derivative of this, so this will become 0.5 with respect to L, so this is 0.5, this is minus 0.25, 0.25 K 0.3 L. Now 0.25 minus 0. Minus 1, that is minus 1.5. Similarly Q L K. Now differentiating this with respect to K, so this will also come out to be this one, that is 0.15 K minus 0.7 L minus 0.5. You can check this out because by Young's theorem we know that QKL is equal to QLK. That means cross partials are same. Now we have to form the Hessian matrix. The formula is same here. We form this H2 is same here, which is H. So the second border partial minor is same, which is this one. So this comes out to be, now we have 0 here, and we have to also take the partial derivatives of this objective, this constrained function. Now the derivative of this constrained function, that is ck, means differentiating with respect to k. So this comes out to be 6. So I will write here 6. I will write here, this is 6. So this is 6. Similarly we have cl. So with respect to l we have this 2. So I will write here 2. Similarly it is here 6 and 2. Now we got the second order derivatives. Now QKK is our, that is 0.21, that is here minus 0.21 minus 0.21 K minus 1.7 and we have this L 0.5. Similarly this QKL, now QKL is this 0.15. so I write here 0.15 K to the power minus 0.7 L minus 0.5. Similarly we have QLK, which is also this 0.15 K minus 0.7 L minus 0.5, and QLL, which comes out to be this minus 0.25 K 0.3 L to the power minus 1.5. So this is our Hessian matrix. Now expanding this along the first row. Now here 0, we have to delete this row and this column and take determinant of this remaining element, remaining determinant. Now 0 multiplied by this remaining determinant will be 0, so we will not solve this for the first element because this will come out to be 0. Now this is, now we have minus 6. We have to delete this row and the column and take determinant of the remaining element. So here it is 6 multiplied by minus 0.25 K 0.3 L minus 1.5 minus 2 and multiplied 0.15 K to the power minus 0.7 K sorry, it is L minus 0.5. So I hope my calculations are getting right here. Similarly we have this plus. Now deleting this row and this column, we take these two elements. Now this is here 6 6 multiplied by 0.15 k to the power minus 0.7 L to the power minus 0.5 minus 2 into this, 2 into this, we have 0.21 k minus 1.7 L 0.5. Now solving this, will come out to be, this is here 6, I write here 6. Now this 6 into minus 0.25, this is 6 5s are 30, 6 2s are 12, 13 14 15, so this is 1.5, so I will write 0.15 k to the power 0.3 L to the power minus 1.5. Here it is minus, now this will become 0.3 k to the power minus 0.7 L to the power minus 0.5 plus 2, we have this 2. Now multiplying these two, this will become 6 into 15. Now this is 6 5s are 30, 6 1s are 6, 7 8 9. So this will become this actually becomes 6 5s are 30, 6 1s are 6, 7 8 9. This is 0.9, actually 0.9 multiplied by k to the power minus 0.7 L to the power minus 0.5, and I am not sure whether my calculation is getting right or wrong. I am sorry for that, because it gets too messy. Here it is minus 2 into 0.21, that is 0.42 k to the power minus 1.7 L to the power 0.5. Now further solving this, this will become, sorry, it is here minus, so this comes out to be 6 into 0.5 this comes out to be, sorry, it is here 1.5, actually I got it wrong. This is 1.5 minus 1.5, so this 6 into minus 1.5, this is 9 k to the power 0.3 L to the power minus 1.5 minus this will become 6 into 0.3, so this comes out to be 1.8. Now minus minus is plus, k to the power k to the power, what we have here, k to the power k to the power 0.7 and L to the power minus 0.5, and we have this plus 0.9 into 2, that is 1.8 k to the power minus 0.7 L to the power minus 0.5, and now this 2 into this will become minus 8.4 and 2 2s are 4, sorry, it is actually 0.84 k to the power minus 1.7 L to the power 0.5. Now this comes out to be, here it is 1.8 0.7 L to the power minus 0.5, and here it is 1.8 minus 0.5 this is 0.5, actually it is here minus 0.7. Now these two terms are same, that means we can add them also. So we got 9k to the power 0.3 L to the power minus 1.5. now 1.8 plus 1.8, that is equal to plus 3.6 k to the power 0.7 L to the power minus 0.5 plus this 0.84 k to the power minus 1.7 L to the power 0.5. So I am not sure whether I have made this calculation right or wrong, because I am doing this manually. There can be errors. If there are some, you can tell me where they are. Now here our H2 is, since these are all the positive terms, that means this will come out to be greater than 0. So this is greater than 0. So when our second bordered principal minor, this H2 is also called second bordered principal minor. Now when our second bordered principal minor is greater than 0, we say H is negative definite. Negative. When H is negative definite, we say that Q is maximized. So here the second border principal minor was greater than 0. When this comes out to be greater than 0, we say H is, this Hessian is negative definite, and the negative definite Hessian is the sufficient condition for the maximization of the this constrained optimization function. Sorry for my mistakes here. You can it gets here messy. If there are some errors, you can ask me where they are, so I could rectify in the next videos. So I hope I make myself clear. Thank you. So I just give a brief recap. We were given a Cobb Douglas production function. This is our Cobb Douglas production function. With the constraint, we were told to find the critical points and check second order condition. Now the critical points are founded. First, we have to form the Lagrange's function. We formed here this Lagrange's function, and we partially differentiate this Lagrange's function with respect to k, l, and lambda, and set them equal to 0 simultaneously. After that, we solve these three equations to get the value of L and K, that is the optimum labor and optimum capital, which comes out to be 124 and 24. So these are our optimal combinations. Now we were told to find the second order condition. The second order condition is used to be sure that we got the maximum points. Now we used the Boarded HESSIAN method in checking the second order condition. We formed a matrix of the second order partial derivatives of this it is said this Lagrange's function, that is, these are the second order partial derivatives, and these are bordered by the first derivatives of the this constrained function. So this was our constrained function actually, and after that we get the we put the values of these derivatives in this. After that, we solve with respect to the first row. Since the first element is 0, we didn't bother to solve for that. So since this first is positive, this is negative. This negative comes from this law of the minors. The law of cofactors. This comes out to be minus 6. This minus comes from the law of cofactors, and this is then plus. So when solving this, we got this this expression, which comes out to be I hope this is greater than 0, because these are all the positive elements here, and when we will add them, so this will automatically get greater than 0. When our H2, that is second border principal minor, was greater than 0, we say that H, the Hessian, is maximized or H is negative definite. So this was all about this. I hope you get this. Thank you. So for more videos on mathematical economics, please subscribe our YouTube channel Econ Maths. Also like, comment and share if you like this video. Thank you.